All right. So it's good to see everybody. We're at the end of another week. In fact, a week from now, in just a few hours, we're going to be on vacation. So all we got to do is get there. But let me go ahead and tell you what's going to happen today into next week. So we're going to go ahead and finish up 2.6 today. Now on Monday, the 2.5 homework is going to be due. So I do want to take a look at one of the problems today before you leave. After that, we'll be on SEL going into next week. Monday, we'll go ahead and start 2.7. So my goal is to go ahead and get 2.7 and 2.8 done before we take off for spring break. Okay, that's going to be my goal. And then when you picked up today, one of the papers is the homework assignment for 2.6. That's going to be due next Wednesday. We'll talk about it at that point. And then the other paper, this Trig crossword puzzle, that is the extra credit activity if anybody's wanting to do that. So I've already posted it to the website as well. But basically, if you go ahead and complete it correctly, get it turned in by next Thursday morning, 8:05, then whatever your lowest exam grade, bless you, is, I'll add 10 points to it. Okay. So if anybody wants to participate in that, you can definitely do so. The only thing I want to make sure and remind you of is coming up on Monday the 10th from 5 to 7 over at Coronado. We have the second AP prep session. So we're going to be talking about exponentials and logs and then graphing trig functions. So if you need to show up late, if you need to leave early, as long as you're able to make it, we'd love to have you there. So let's go ahead and get to it. Did anybody need a copy of 2.6? Okay. Well, we were talking yesterday about comparing data sets. Are they linear, quadratic, or exponential? And we're going to use a linear model when the data reveals a relatively constant rate of change. Now, in previous lessons, we were looking to have the exact same constant over and over again, but now we're looking more in a contextual sense, real-world applications, and unfortunately, the real-world data isn't always going to be perfect. So we're looking for a relatively constant rate of change. If it's quadratic, use a quadratic model when the rates of change are increasing or decreasing at a relatively constant rate. We actually looked at this in a previous lesson. But yesterday, we were kind of focused more on the data generally following a U-shaped pattern. So what that means is we should somewhat be able to see symmetry through the Y values. Okay, like here, 9 and 8.8, 3.95 and 4.2 are pretty close to each other. So either the values are going to decrease and then increase, or they could increase and then decrease with these values being very similar. And then exponential is what we've been talking about a lot lately. Use an exponential model when the output values are roughly proportional. So what this means is that each successive output is approximately the result of repeated multiplication. All right, and then we did some examples, and everybody seemed to be pretty good on those. Now, I brought up the idea of residuals again. Okay, so a residual is simply the difference between an actual output, that value from the data table, and your predicted output, which came from our regression model. We went ahead and did another example with the weight of babies, but here is how we're going to finish up our 2.6 notes, using a residual plot to check the appropriateness of a model. Okay. So here's how this works. A residual plot shows all the residuals for a set of data and can be used to help determine if a model is appropriate for that set of data. Now, if a model for a given set of data is appropriate, the residual plot should appear without pattern. And I know that's kind of weird, but in mathematics, we're always trying to identify the pattern so we can establish what's happening. But when it comes to a residual plot, it's actually good for us if there's no pattern. Okay. In fact, if you do see a clear pattern in the residual plot, then that means your regression is not appropriate. You don't want to use that model. Okay, so let's look at an example. Now, this is a residual plot. I'll go ahead and say that the table to the right, this is not what created that residual plot. I just wanted you to kind of see an idea. We've got X and Y values. You've got your predicted Ys and then your residuals. Well, this is how you would plot these points in a residual plot. The X value coupled with its residual value. Okay, but that table is not what gives this particular plot. So example 3, an exponential regression was used to model a data set. The residual plot for the exponential regression is shown above. Which of the following is the best conclusion about the appropriateness of the exponential regression model based on the plot? Okay. Well, do you see a clear pattern in the points, or is it just random? Looks to me like it's just random. So this is what we want. If it's no pattern, okay, then that means it's got to be appropriate. Okay. And then we're going to say it's appropriate because there's no pattern. That's all there is to it. Okay. When you're looking at a residual plot, it's good if there's no pattern. It's actually bad for us if there is a pattern. That means your regression model isn't going to work. Okay. Well, let's try another one here. Okay, so example 4, a group of AP Pre-Cal students used a set of data to create linear, quadratic, and exponential regression models. After creating the 3 models, the students created a residual plot for each model type, shown above. Based on the 3 residual plots above, which model was the most appropriate? Give a reason for your answer based on the residual plots above. Okay, well, let's just go through these one at a time. Okay, linear. Okay, is there any clear pattern there? What do you think? Does it appear to be random? Is there a pattern? There's definitely a pattern. I can easily go ahead and put a smooth curve through these points here. Okay, so it's not linear. Let's take a look at quadratic. What do you think? Pattern or no? Yeah, there's a definite pattern. In fact, it almost looks to me to be a polynomial. Okay, so if it's not linear and quadratic, it has to be exponential. It's the only one that has what? Random, so no pattern. Okay, and that's pretty much the big idea for the last part of these notes. Any questions? Try not following? It's pretty easy, right? Okay, and just like that, we're down to our last question on 2.6. So Mr. Passwater hopes to make it into the Guinness Book of World Records by painting the world's biggest mural on the sides of several downtown buildings. His mural will consist of many painted circles of various sizes, where each circle is painted a different color. He wants to create a model to determine how much paint is needed in quarts for a circle of radius r, which is in feet. So part A, should Mr. Passwater use a linear, quadratic, or an exponential model in this situation? Now, I've already got my statement ready to go. He should use a blank model because the amount of paint depends on the area of each circle given by the model A of r equals blank. Okay, so what are we thinking? Linear, quadratic, or exponential? Okay, I heard quadratic. Why? Area of what specifically? What's he wanting to paint a bunch of? Circles. That's exactly right. And if you take a look at it, I mean, we find the area of a circle by using pi r squared. To us, it's always a formula, but it is a quadratic function. That's absolutely right. Okay. So he's going to use a quadratic model. Okay. Now, after creating his model, Mr. Passwater uses it to purchase different special paint colors to use on his mural. If in this situation, do you think it's more appropriate for the model to under or overestimate the actual amount of paint needed? Okay, I would overestimate, but why? Basically, yeah, that's good to have extra. I mean, that's the mindset I would go into. Overestimation. I've always been in the opinion that it's better to have it and not need it, okay, than need it and not have it. Okay. All right, you're absolutely right. Because he doesn't want to run out of paint. He wants to get in the Guinness Book of World Records. All right, and with that, 2.6 is done. Okay, we did not have a whole lot left. Any questions? Okay. All right, so while I go ahead and set this up for the next class, if you will go ahead, pull out the assignment for 2.5. I want to go ahead and do one problem on that before we call it quits today. All right, back to where we were. Okay, so specifically, I want to take a look at 2.5, number 2. Did anybody need a copy of the assignment? Okay. Now, the reason I chose number 2 is because there's a couple of things we did earlier in the week in the notes that I really want to make sure to bring your attention to. Okay, so this one, it says, before Facebook, we, the old people, had MySpace, the first social networking site that reached a global audience. At its peak in 2008, MySpace was averaging over 100 million daily visitors. However, as Facebook rose in popularity, MySpace became less and less popular. The table shows the number of daily visitors to MySpace in millions, months since January of 2009. Okay. So I'm kind of curious, how many people in here have a Facebook page? It's pretty much been the same thing. So is it pretty much viewed that Facebook is simply for older people? Okay. Well, would it surprise you that I don't have a Facebook page? So that means it would surprise you, but that means I'm not old, right? Okay. Okay. All right. So what is it that the younger generation uses? Instagram? Okay. Okay. Just curious. Just curious. Okay. So part A, use the data in the table to create an exponential regression model that looks like y equals a times b to the x, where y represents the number of daily visitors to MySpace in millions and x months since January of 09. Okay, so we're going to go through the keystrokes again to put the data in the calculator. All right, so let's pull out our calculators here. I'm going to go to my home screen. What do? I always forget. Okay, lists and spreadsheets. So I can go ahead and choose new and then lists and spreadsheets. And just go ahead and let you know down here in the very middle, that is also your spreadsheet icon. You can just click that and it'll take you right to it. But I'll do it the old fashioned way. If there's anything in there, we're not going to save it. Lists and spreadsheets. Okay. So this time we actually are using X and Y. Remember to avoid the equals row. All right, let's put in our data. So 0, 6, 15, 18, 24, 30, 39. Okay. Control 7. And let's put in the corresponding millions of people. 25, 20.5, 13.5, 10, 5.5, 2.6, and finally 1.7. Okay. So I got my data in. Well, I'm going to go home. What do I choose now? Okay, data and statistics. So I want to choose this icon down at the bottom. Looks like a bar graph. Okay. Now remember, we have to tell the calculator how to organize the data, and you're welcome to use the touchpad on your calculator to choose where it says click and add variable. I like to use the tab. Okay, take care of the first column, the horizontal first, so X. Then I'm going to click tab. We're going to choose the vertical. And there we go. We're wanting an exponential model. So I know I hit menu, but where do I go from here? We want analyze, regression, and then we chose exponential. Here we go. Now, when I write my answer or my equation, I'm going to go ahead and take it to 4 decimal places because that's the maximum number I have here. I'm going to take more than 3 because I know what we're about to do in part C. And I'm looking for as just an accurate as possible an answer as we can get. So I'm going to come on back over here. So here's my function. We ended up with y equals, I believe it was 31.6016. Am I correct on that? Okay. And then we had 0.9282 to the x power. Okay. Okay, so y is in millions of users, and then x is months since 2009. There's my function. Okay. Well, B, based on the model we have, how many daily visitors did MySpace have after 20 months? Okay, well, they're giving me the amount of time x, so I'm just going to go ahead and plug that right in. So this one's easy. Okay, let's come on over here to the calculator. Okay, go home. Okay, so that was 31.6016 times 0.9282 to the power of 20. Okay, so somebody help me out here. What should I get when I push enter? 7.12099. Okay, now remember, this is meant to be in millions of people, So I'd go ahead and say 7,120,990. Okay, so 7,100 and what was it? I just said 20,990. 120,990 people. Okay. Now here's the part of the problem that I really wanted you to notice. Okay, this is part C. Okay, so I'll go ahead and scroll up here. So it says, let y equals ab to the t be an equivalent form of the model found in part A, where t represents the number of years since January 09. Find the values of a and b. So I want to take this form here, so a times b to the t, and I want to set it equal to the model I have, 31.6016 times 0.9282 to the power of x. Excuse me. Okay. Now, we're looking for A and B. One of these is going to be really quick. Which one do we already have, A or B? Not quite. We have A. Okay, we have the leading scale factor. So I know that A has to equal the 31.6016. Now, in order to find B, we want to go ahead and focus on these parts with the base here. So B to the T has got to equal 0.9282 to the x. See, unfortunately, we have different powers, which is why I can't say that B is just equal to that decimal. Now, there's also another problem here. How do we measure x? Or not years. X is the number of months, but now you're absolutely right. We measure T in the number of years. So we're going to have to rewrite T in terms of X. Okay. So I'm going to give you a couple of minutes. I want you to go ahead and figure out what is the base in this other function. Okay, let me get my timer here. Of course, it disappeared. Here it is. Okay. Now, if you want me to go ahead and check your answer, we'll go ahead and round it to 4 decimal places, just like we did before. Okay. So let's see who can get that. If you're looking for a hint, I would go ahead and use one of those exponent rules that we were talking about recently. Of course, this is after you rewrite T. Okay, once we're done with this, we're on SEL. Yeah, there will be some blanks.
Like I was last week.
If it's a space between words, yes. Anybody think they got the value and you want me to check it? All right, that's 2 minutes. I will say that only a few people, definitely a handful, have gotten this answer correct, which is why I wanted to look at this in the first place. Anybody want me to check before we do it? Okay, here's what you should be getting. B is equal to 0.4090. Okay, anybody get that? Really? Hey, why didn't you want me to check your number? I have that confidence, okay. Good, good, good. Anybody else? Okay, so the first problem, we have to go ahead and make sure that we got the right units. Remember, X is in months, T is in years. So if I rewrite T, I'm going to say X months divided by 12. Okay, because every 12 months, you got yourself 1 year. All right, so here's what we have. B to the X over 12 equals 0.9282 to the X. Okay, so how am I finding that B is equal to 0.4090? What would I do? Or what exponent rule was I even referring to? The product? Like, what do you mean? So you want me to raise both sides to the... Oh, I see what you're saying. Okay. So you want me to rewrite this as B to the 1/12 to the X power? Or did you say the reverse? It doesn't matter? Okay. So 0.9282 to the X. Okay. And you're absolutely right, because now that they have the same power of X, B to the 1/12 should equal 0.9282. So if B to the 1/12 equals 0.9282, how do I get B and get rid of the 1/12? There you go. Let's raise both sides to the 12. So if you take your calculator, 0.9282 to the 12th, that's how we got that. All right. Questions? Was anybody close? Oh, 12th root. Okay. Okay. Well, there we go. We are done. Okay, what'd that take us? A little over 22 minutes? That ain't bad. Okay, let me go ahead and get this ready for the next class. We should